Hello, everybody. Dr. Bianchi here, and in this video, I am going to summarize measures of central tendency. You can find this content in Chapter 3. You can also find the PowerPoint slides uploaded separately as a standalone document that you can download. Measures of central tendency are one class of descriptive statistics that we use to help summarize and organize data. Let's go ahead and look at what central tendency refers to. The term central tendency is a statistical measure, and basically the purpose of measures of central tendency is to find the single score that's most typical or that best represents how the entire group performed on some kind of test or assessment. Now, there are three measures of central tendency that you may see used in research. The first one is the mean or the average score. You may also be familiar with the median and the mode. Those are the three measures of central tendency that we'll be looking at in this video. One thing to keep in mind is that the goal of central tendency is to describe your data most accurately. And depending on how your data are actually shaped and what your results look like, one measure of central tendency might be more or less preferable over one of the others. Here is a good visual just kind of demonstrating the fact that identifying the center of a distribution of scores is not always as straightforward as you might perceive. Over here on the left, we have a perfectly normally distributed set of data. Okay, most scores clustering in the middle with fewer people scoring on the extremes. Okay, each one of these boxes is an individual and you can see where they fall. Conceptualizing the center of this distribution is fairly simple. Okay, the average is going to be 5, and that's a really good representative measure of how most people performed. Okay, it fits the data pretty well. Over here, though, things are a little bit more complicated. We have negatively skewed data with the tail dragging out towards the lower numbers and then piling up here. Now, if you were to calculate the mean score for this set of data, you'd probably get something between 5 and 6, but as you'll see, a lot of people scored quite higher than that. So here, the data is skewed in a way that kind of distorts the mean. This would be a situation where reporting the median might also be useful, as well as the mode. Okay, here we have what's called a bimodal distribution. We basically have two groups, okay, people performing, and they're separating into their own clusters. You can imagine that this is the first exam, and up here are all the people that studied, and down here are the people that missed class and didn't study, with nobody falling in the middle. Here, the mean and the median would be really misleading because there'd probably be some values in here, and no one even scored those values. This would be a case where you would want to report that you have a bimodal or double peak set of data, and you would report the most popular scores on the low end, the mode of 2 and the mode of 8. Okay, but I put this up just to really demonstrate that defining the center of the distribution, giving a number that's most representative or most typical of the data is not always cut and dry. Okay, you really need to look at the way your data are shaped and say, okay, which one of those three measures of central tendency is going to give the most legitimate and accurate description of how my data actually look. Okay, different distribution shapes require different conceptualizations of center. You're going to want to choose the one which best represents the scores in your given situation. Okay, the mean is a fancy word for average. We've all calculated averages before. If our average electric bill for 1 month is 20, the next is 30. We take the average, 20 plus 30 is 50. Divide that by 2, we have an average electric bill of 25. Okay, we can add a third month of 100. Okay, then we end up with an average electric bill of $75. Okay, 150 divided by 3. Here are the formulas, the formal mathematical formulas for computing the mean score, which we just did on the previous slide. Okay, now you should get used to a distinction that's going to come up over and over again in this class. When populations are being discussed, you're going to see Greek lettering. Okay, Greek lettering is a signal that the formula is for a population. Samples, you're going to see, regular types of letters. These formulas are mathematically equivalent. Okay, calculating the mean or the average is exactly the same for populations and samples. Okay, there will be formulas later on in the course that differ for population and samples. But basically, we sum up all of the raw scores and we divide by the number of scores in the data. Okay, this is the summation sign. It means add everything up that comes after it. Okay, these formulas are found on the formula sheet. Now we can look at the mean in 3 different ways. Okay, the sum of scores divided by the number of scores in the data. We just did that with the electric bill example. The amount of something that each individual receives when it's divided equally among all of the individuals in the distribution. Okay, if I have $3,000 and I have 3 people, well, everybody gets $1,000. We can also talk about the mean as being a balance point for the distribution. Let me show you what this means. Here we have a set of data where the population mean is 5. And each one of these blocks represents an individual and where they scored on this test or assessment. The mean can be thought of as balancing the distances. Okay, here we have 2 people who have scored a 6. A 6 is 1 point away from the mean of 5, and there's 2 of them. So these 2 individuals produce 2 difference points totals. Okay, there's a 2-point deviation here, okay, from the mean. This person up here with a score of 10 is 5 points away from 5. They have a deviation score of being 5 above the mean. You'll notice that we have a combined deviation of 7 points on the right side of the mean. Now, if we look below the mean, we have one person who scored a 2. Okay, 2 is 3 points below 5. This is a 3-point deviation from the mean. And then this one individual here who scored a 1 is 4 points away from the mean. On this side of the seesaw, if you want to look at it that way, we also have a 7-point deviation. The mean is balancing the distances on both sides. Okay, this is another way to think about the mean as balancing out the distances or the deviations of scores. Now, the mean is extremely susceptible to changes in the data and is especially sensitive to extreme values. If this person with the 10 was not in the data and were cut out, the mean would likely shift down. Okay, it is actually being pulled up because of this person out here sitting at 10. If they were eliminated, the mean would go down. Okay, the same can be true if we eliminated the people over here. Okay, if these scores weren't here, the mean would then shift up. So the mean is extremely sensitive to changes in the data and to extreme values. Okay, it moves with the addition and subtraction of values. Now, sometimes we don't just want to calculate a mean for one sample, but we want to calculate a mean for 2 samples. This is called a weighted or a combined mean. And basically, you're just doubling up on the original formula to calculate an average by adding in the second sample. So here we have the overall combined mean formula is equal to the sum of the scores for sample 1 plus the sum of all of the scores for sample 2. And then we're going to divide by the sample size for sample 1 and the number of people in sample 2. This is why this is called a weighted mean. The sample that has more people in it is going to contribute or be weighted more towards producing that mean. Okay, let's go ahead. You can feel free to pause the video here. I would like you to go ahead and compute the weighted mean for these 2 samples using the weighted mean formula. If you haven't already downloaded the formula sheet, that's where you will find the formula to compute the solution. Okay, so feel free to pause the video if you need a few extra seconds to go through this. Okay, but basically you should have gotten a mean of 6.4. In your numerator, you should have had this addition of 72 plus 56, which comes out to 128. And your numerator should have been 20. There's 12 people in sample 1, 8 in sample 2. 12 plus 8 is 20. We get a mean of 6.4. We can also compute a mean from a frequency distribution table. Here are quiz scores. Here are the frequency of those scores. If we create a third column where we times x by f, we get a column called fx. And we can sum all of those up. Whoops. We can sum all of those values up. The total value of the x values combined is 66. 8 people in the study. 66 over 8 is 8.25. The average or mean score for this data is 8.25. Okay, so a frequency distribution gives you the values that were obtained on some kind of test or assessment. It gives you the frequency. And by calculating an f by x column, you can get the total summed value for the x scores, and you can divide by the sample size to get the mean. Okay, here's a practice question for you. Go ahead and see if you can take this frequency distribution table and come up with the average score. Just like in the example before, you're going to need to times x by f and create a third column here, fx, and then add those values up to get the sum of the x values. Then you'll divide by the sample size, which you get by adding up the frequency column. Okay, take a second to do that. Okay, if you go through with that, you should end up with a column that looks like this. And 32 divided by 12 is 2.67. The mean for this data is 2.67. Quick question here. A sample of 12 scores has a mean of 8. What is the value of the sum of x for this sample? This is a simple trick. You just multiply 12 times 8. You can work backwards in that way to get the sum of x, which is 96. What are some characteristics of the mean? Key takeaway point, the mean is sensitive to changes in the data. Changing the value of a score usually changes the mean. The mean is extremely susceptible to outliers, extreme values in the data. The mean is susceptible to skewed data. Positive and negative skews pull the mean in that direction or the other. Introducing a new score or removing a score changes the mean. The mean is a democratic measure of central tendency. It is a measure that takes into account all of the data. The only exception to that is if the score added or removed is exactly equal to the mean. So if the mean of a data set were 2.67 and you added a score of 2.67 or removed a score of 2.67, that would not change the mean. If you add or subtract a constant from each score, that will change the mean by the same amount. If we subtract 2 from every single value, the mean will also go down by 2 points. And the same thing is true if we added a constant amount. Same thing with multiplication and dividing. Okay, if we multiply or divide each score by a constant, okay, let's say we multiply every score by 2, the mean will also be multiplied by 2. Now you may be asking yourself, when do these kinds of scenarios ever come into play? Sometimes when we engage in some predictive modeling, where we try to predict the outcome of a treatment that's been well studied, we have some hypotheses and ideas about how much improvement is typical, and we can do that forward type modeling. Okay, the mean is highly sensitive to changes in scores. If I pile on a couple of more people with an 11 or a 12, the mean is going to get pulled up. In contrast, if I pile on more people scoring 2s, 3s, and 4s, the mean is going to shift down. The only way that this mean wouldn't change is if I added a 7 here, it would keep the mean at 7. Okay, a sample of 7 scores has a mean of 5. All of the scores are doubled. What is the new mean? Well, the mean must also double, right? So the mean is equal to 10. Now I want to spend a little time just summarizing the median. Okay, the median is another measure of central tendency, and It's the midpoint of the distribution. It separates the distribution into the top 50% and the bottom 50%. We get scores divided into two groups of equal size. Now, a key takeaway point that you should have in your notes is the median is very good to use as a measure of central tendency when you have skewed data and when you have extreme outliers in your data, because the mean is not impacted by these things. It is resistant or robust to outliers, extreme values, and to skewed data. Okay, what is the median? It's the middle score. Okay, everyone probably remembers this from former math courses. Here we have a data set, 3, 5, 8, 10, and 11. The middle score is 8, the median is 8. Okay, 50% of values above the mean, 50% below. If we have an even set of numbers, we just take the average of the two in the middle. Here we would take the average of 4 and 5. We get 4.5. Now, I'm not going to spend a lot of time going into this, but finding the precise median for a continuous variable can be a little bit more tricky. Remember, a continuous variable can be infinitely divided, and sometimes identifying the precise median involves locating the interval and including the real limits. Okay, so sometimes it's necessary to determine the fraction of an interval needed to divide the distribution exactly in half. Here's a formula for doing that, okay, and here's just sort of a picture of this. With 8 scores, the median should have 4 scores below and 4 scores above it. 3 scores fall below the upper real limit of 3, okay, 3.5. So the number of scores needed to reach 50 is 1 more score. Because 4 scores fall in the interval of 3.5 to 4.5, a fraction needs to be taken here. Okay, so sometimes calculating the median can be a little bit more complex when you're working with continuous variables. Just be aware of this. I'm unlikely to ask you questions about this, but if you're running statistical analyses using computerized software, you really don't have to worry about this. The mean is the balance point of a distribution. It's based on distances. The median, in contrast, is the midpoint of a distribution. It is defined by the number of scores. Both of these measures of central tendency use 2 different concepts of the middle to describe the data. Almost always when you're working with numerical data, you will report the mean. It is the most commonly understood measure of central tendency. It's the most frequently reported. However, if you have extreme values or you have skewed data, you might also want to supplement the mean with the median to give a better overview of how your data look. Here's an example. Here we have a frequency plot, and you can see most people scoring around 2 or 3. But we have this one person all the way out here at 12, pulling the mean up. The mean is 4. Okay, if this 12 was not in the data, the mean would likely shift somewhere in here. The mean is being pulled up by this outlier. However, it has no impact on the median. The median will remain 2.5 even if this value was 100. Okay, because the median splits the data set into the bottom 50% and the upper 50%, you can see that it's not impacted by extreme values. Okay, a 12 is above and in that upper 50%, in the same way a score of 1,000 would be. Okay, so the median is great because it's resistant and robust to extreme values in the data. Okay, I'm going to skip through these. The last measure of central tendency I want to bring up is the mode. The mode is the most popular score. The mode can be used with any scale of measurement, but it's important to realize that it's most commonly used when we have nominal or label type data. It's not possible to calculate an average for what color car people have or whether they're right or left-handed. In those kinds of cases where we have labels, differences in kinds and types, not in degree or quantity, we're going to want to report the mode. Okay, the mode for the color of pen in Psych 230 is black. Most people are writing with a black pen. It's the most popular color. The mode can be used with numerical data as well. You typically see that when you get a bimodal or a double peak set of data. Here, the mean or the median would be misleading. It'd be somewhere in between 4, 5, and 6. Okay, in this case, you'd want to report that you got a bimodal distribution. The lower mode is equal to 2. The upper mode is equal to 10. This was a hearing test. You can imagine these people were wearing their hearing aid that day, and these elderly folks were not wearing their hearing aid. People either acing the test or not doing so well, very few in the middle. Okay, a bimodal or a bi-peak distribution. Okay, I've posted the video of the toads on D2L. Okay, just kind of a cool, kind of funny animation summarizing the mean, median, and the mode. So feel free to check that out if that's of interest to you. This table is extremely useful. It is a summary of this lecture video. We have 3 measures of central tendency that we've covered, and they may be appropriate or misleading under different situations. I highly recommend pausing the video and walking through this table. This is a great place to come if you have a question on measures of central tendency or are unsure about what measure to report in your own research. Here is a complete overview of the pros and cons of the mean, the median, and the mode. Remember, the measure or measures of central tendency that you choose to report really are based on the way your data is shaped. Okay, these measures of central tendency conceptualize the middle of the data or the most typical score in slightly different ways. Okay, we can also graph means and medians in a line graph. Here's a drug dose study, placebo group, low dose, low to mild dose, medium and high dose. Okay, what is the impact of this drug on food consumption? This was an obesity study. Does the drug work? Well, if you get the dose right. Okay, it appears that dose 3 is the most effective. If you overdo it, you start to shoot back up with more food consumption. It appears low doses are not as effective. Okay, so just an example of how we can graph and display means easily in a plot. Here's medians being graphed. The median cost of a new house in the thousands of dollars. Okay, depending on where in the United States we're talking about. We can look at this graph. The quick takeaway point is that it's expensive to live in the Northeast and in the West. Okay, just some visuals walking through different kinds of distributions. When we have a perfectly normal distribution, by definition, the mean, the median, and the mode are the same. Here we have the bimodal distribution that has 2 modes, okay, with the mean and median falling in the middle. And here's an example of no mode. All responses are equally probable, the mean and the median sitting in the middle. Okay, this graph, these graphs are basically showing you what happens with skewed data. Okay, here we have a positive skew. Okay, this curve deviates from perfect normality, and the mean gets pulled up with the skewed tail. Okay, the median is resistant to being impacted. The same is true over here where we have a negative skew. The mean gets pulled down with a negative skew. So the long and short of it, the mean is impacted by skew in the data. I'm going to go ahead and skip through this. That is going to wrap up the summary of Chapter 3. Okay, feel free to check out the PowerPoint slides that are uploaded as a standalone file and contain notes in the notes section. And I will see you in the next video. I hope everybody has a great rest of their day.